All right, welcome back. What we're doing is the calculus of variation 1. We'll have a complete playlist eventually. We're just starting. What we're going to do today is real numbers and notation is what we were doing. And specifically, last time we did sets and operations on sets, which create new sets from old sets. And then I messed up the example at the end because I tried to change the T. We're going to do a proper example with the Venn diagrams. I'll have an S and a T and an R. One will be a subset, one won't. So I can do disjoint, unions, etc. And then let's talk about, after I do that, because we talked about last time a little bit about binary operations of numbers or elements in sets and then binary operations on actual sets themselves, I'll do a tangent, pun intended, towards binary operations which create new stuff from old stuff. This will be like functions and or elements that functions move around. And then we'll talk about binary relations, which are true or false. Either I'm related to you or not. That's a blood debt. You can't get out of that one. And then finally, well, I'll do this one fairly quickly, and then we'll do a separate video about those ones and what a function actually is. And then set builder notation. And we'll start finally finishing off this chapter or section, which is the real numbers. Let's get to it. All right, so let's do an example properly. I have S is 1, 2, 3, 4, 5, 6, 7. Just like last time, I did say correctly. Eventually, what we're going to do at the end of this video is set builder notation so that I can use this to describe the more complicated numbers like rational numbers, which are the ratio of two integers, and I need a more complicated way of describing them. And you're going to start with the curly brackets and then build it, because if I wanted to list the first 8,000 numbers, I don't want to write 1 to 8,000. We'll never get there. It'll be a whole video where I should let's do an 8-hour stream where I just list numbers, start counting, and see how far I can go before I go insane. Yeah, note to self. Now T is going to be not exactly a subset of S, like where I screwed it up last time. I started changing it, so I've got 2 of them. But notice right now, T is the first 5 odd prime numbers. 2 is the loneliest number if you're talking about primes. R is now going to be, note, is a subset of S. And let's see what happens to union and intersection when they're a subset, and then union and intersection when they are not subsets of one another. That was the point, and then I screwed up last time because I tried to just use one set and then change it halfway through the roll. Stick to your guns. Now find what? Here's how I scare you now. So 1, how many combinations are there? Oh, and remember, this guy is empty set. And I'll write it out. The empty set is a subset of every set. So R is going to be a subset, but then I'm going to try and trick you or catfish you, and don't let me already. R is a subset, so when I do the union and intersection, what happens? And then can you do that for when I do R intersect the empty set and R union the empty set? What's going to happen? Well, he's a subset of everybody, so it should tell you what happens when I do R and S. Let's go. This is vacuously true. What this is saying is if you're in the empty set, then you're in any arbitrary set. Well, that has to be true because this is false. There is nobody in there actually. So I can do anything with a false antecedent. I can prove anything. If I'm the king of France, I have $1 billion in my bank account. Is true because I'm not the king of France. So that's what vacuously true is. You can look it up, whether I spelled that right and what vacuously true means. It's true by default because a false antecedent implies any conclusion. I digress. 1, 2, 3. How many do we have then? So I can do S union T, S intersect T, S union R, 4, S intersect R, 5. I can do, no more S's. I fixed the S first is how you do combinatorics. Then I ran through the other guys. So now I need T union R, and 6. I need a screw for the whiteboard. T intersect R, and then what was I going to have? 6, 7. Roman numerals are silly. I want R union empty set, and 8 is R intersect empty set. And then correctly, 1 before decim. That's what got me last time. Stop that. It's talking to the pens again. All right. Now let's magically make this disappear. 1. I don't remember what I used. I fixed S and rotated through T and then R. So S union T should create something in general bigger. Now what I'm going to do is look at our universe of discourse, which is, I always wanted to write that one, but I'll rotate it for you, Sean. And the natural numbers for now, the big guys. Now I have an S and a T. Let's do first. The union should create the dividing cell, the whole thing. So let's see if that's true. Why? Because if I look at that before I start, let's give myself a fighting chance with that. You'll see what I'm talking about in a second. Oh. So and then I have so when I do this now in my mind, I just had to, you saw me do it in front of you. But this is called a Venn diagram, and it will help you pictorially represent or geometrically draw a picture is the mantra. Thank you, Mark. Even when you're doing set theory, it'll help your monkey brain understand what the heck is going on. S union T should create something bigger, so it's going to create, I can just get rid of these in a real painful way for you. I'm enjoying myself thoroughly. So I can get rid of those. It's like I'm going to mute you. And it should create a bigger set in general because it's anything in here or in here. So this will be the union T in the Venn diagram. If this was S originally and this was T originally, S union T will in fact be this. I can make it with the squeegee too. Squeegee. So what is this? First just run through S because it's for sure that. And then I look at T, what wasn't in S, 11 and 13, and it created a bigger set. If I'm going to do 2, if I'm going to do S intersect T now in this Venn diagram, I need those back again. And then now, what is it going to be? I have to go through both of them and say, are they both in there? Is 1 in T? No. Is 2 in T? No. Is 3 in T? Yes. So I'm going to keep 3. Get out of the way, and you're next after our tangent. Is 4 in there? No. Is 5 in there? Yes. Is 7 in there? Yes. So that's our overlap, 3, 5, 7. The only or the only triple prime pair where 3, 4, 5, 6, 7. These are all primes, and all they are is consecutively done, which they're also a double twin prime pair. It's the only one that does that. But then we have, this is also one. Put some zeros in there. Is it always? I don't know. That's how my brain works. No, it's probably not. That one's got 1001 has 7 times 11 times 13. No. Well, we'll see. You do it. It's an even palindrome, so it has an 11 in it for sure. 11 is the only even digit palindromic prime. So if I do 1 minus 0 minus 0 minus 1, I get 0, and 11 divides 0, so 11 divides 1001. That's not prime. Not a twin prime pair. Boo! But this one is. Is 1, 3, 1, 3, 3, 1, or 1 bunch of, there's a pattern with that one. It's like, are those ones all primes? I don't know. Let's do another Venn diagram. All right, let's do S union R and S intersect R now. Now that R, first of all, do we have this for every, I'm going to use it upside down. A is for all. Backwards E is there exists. If you want the 2 words for the day or concepts, this is called the universal and existential quantifier, respectively, in predicate logic. Do you want to see some predicates? LXY is read as X loves Y. This may Barney screw you, may not be a symmetric or commutative operation. But let's check out what this says using these guys. What does that say? Requited love exists. There exists an X and there exists a Y such that X loves Y and Y loves X. This is a predicate. So start learning it now. It's 2 more symbols. It's not too hard. And then you can write fancy crap. Yeah, I can ruin even, oh, I can do anything with math. So with these 2 guys, I can predicate. What I want is, and I need this one now. And now you saw that in reverse. Get back here. I want to say for any X in R, is this the question, technically speaking, that X is in also S? This would mean that, whoa, that's not, we're going there, but not yet. You're not even close to R. You're countable finite. No. So what this would say is R is a subset of S this way. And so instead of just saying it is, I should mathematically unwind for you quickly what it's actually saying. So for every X in our universe of discourse, R will be a subset of S if this implies this, which is true. How do you check? Brute force. 2 is in R. Oh, I really want to write 2 of them. Does that mean that 2 is in S? Yes. 4 is in R. Does that imply 4 is in S? Yes. There it is. 6 is in R. So that implies 6 is in S. Yes. So R is a subset of S. There's the proof. That's what we're doing. Oh, where are you? Get over here. So now that I've done that tangent, you're welcome. R is a subset of S. So when you make the bigger guy, or say it can be in either of them, and this one's the bigger one, their union will be the big one, and their intersection, you're now saying which is in both. Well, only the guys that are in the smaller one, so their intersection will be R. Watch what happens. The union is 1, 2, 3, 4, 5, 6, 7. Just list S again, and then now just check. Got it, got it, got it. So done. What is that? S. I'll start doing that so that it differentiates between S and S. Tell me how to write things. Me fail English. Get the clip. Now what am I going to do? Intersection says it has to be in both, so I get the 2. Yes. 3, no bueno. 4, 4, 6, 6. Sacre bleu. 2, 4, 6. This is the smaller guy. R. What does that look like in a Venn diagram? Don't you shut me down yet. I didn't even need the universe of discourse. Doesn't have to look like this. That's R inside S. There we go. Let's do the next ones. That was, sorry, 3 and 4. You didn't index. Yes, I did. Haha, gotcha. Now, rolling. The roof is like right there. Just so that you know. Ooh. All right. Tur. T union R and T intersect R now. We can scrap S. For where we're going, we don't need roads. What do I need? Interval notation and set Buller notation. T is going to be 3, 5, 7, 11, 13, the first 5 odd prime numbers. And R is the first 3 even numbers, 2, 4, 6. And so notice now, if I've done that correctly, that's why I left 2 out of the odd, or out of the primes. R and T have nothing in common. T is all odd numbers, R is all even numbers. They have nothing in common, so their intersection will be the guy I need to create. Who's it going to be? So T union R, anything in. So list T now. 3, where are you going? 7, 5, 7, 11, 13. And then you don't have to be in chronological or lexicographical order at all. Then I just list 2, 4, 6. So it created a bigger. So now watch, I'm going to have to color code T, capital T. And then now, what do I have in T? I have 3, 5, 7, 11, 13, and then I have 2, 4, 6. So what's their union? Their union has to be just this now. This is the union. It made a bigger set in general, but this is what it is going to look like pictorially or on an interval notation in one dimension. If two intervals, if you have this interval from -1 to 0, and then you have this interval from 0 to infinity, and then all of a sudden I'm using interval notation, and it says that this one's open and infinity is not a real number, so how dare you use a square bracket? And then I use square brackets here. What's the intersection of that? These. That's it. Infinity is an extremely long time, especially towards the end. So this is pictorially, if they have nothing in common, that's what it's going to look like, two separated sets. It creates a bigger one, their union, back off. But usually we're interested in the intersection. We want the intersection of two functions. When I add them, what's their domain? The intersection of the original two, because the algebra has to make sense for both of them. So how can I put f of -1 in if this f is the square root of x? If g is x squared, you're like, what are you talking about? If g is x squared, then he can put -1. His domain is R. There's no restrictions. But I can't put -1 into root x plus x squared. So what are you talking about? I need intersections of sets is what I'm saying. You'll see in the videos below. What's their intersection now? I just erased it, you son of a bitch, but I don't need it. Nothing. That's why we needed that. What do you create when you're trying to create sets and they have nothing in common? The set with nothing in it. Him. Now, what was last? Catfish. No, it wasn't last, but penultimate then, grouping. The penultimate grouping. It's not the last supper, sir. It's the penultimate supper. All I said was that halibut was good enough for Jehovah. Stone him. So 8 and 1 before 10, commonly referred to as 9. I don't like him. Screw you, Russians. And your 9s. And your 9s anyways. What was 8? Don't correct me. It was R union empty set and R intersect empty set. And then I had something about subset. Complements. So what is this guy? This should have been, this is what I was talking about. This should rectify itself, go look back, and R was a subset of S. So what should it create? Their union should create the bigger one, the guy that has something in it. Here's the empty set. You want to see what he's got? Who's 1? According to me, anyways. Who's 0? That's why he's a natural number, but whatever. Those are my little flamenco. And now what was the last one? Decim. And on 10, I think. Now we had what is the complement of R in S, which is correct now because I made sure that it was inside there. So now there's S. Let's make it silly. And then what was R? R was this now. So now I just pushed back. I pushed S to the universe of discourse, and I'm ignoring N right now because now I'm talking about in relation. This relation has to be, they don't point these things out a lot of the time, or it's not possibly made clear, even though they're trying to point it out. This relation actually depends on whether they're subsets, and it would be different depending on which subset I'm trying to view him in. So here's R. If this is an egg that I just cracked open, let's make this more realistic. The complement is the white, R is the yolk. All right, I don't have yellow, so screw you. But if this is R, which was 2, 4, 6, what was S? Everything else, everything else. Eat your freaking math. Feed your brain. Janis Joplin. Oh, don't bend down when you do that. I need this thing though. All right, let's do tangent to binary operations, binary relations. So now what we're going to do is we're going to do a quick tangent into binary operations and relations. First, let's do a binary operation on a set S. It specifically, technically speaking, has to reference the set S. The binary operation, you can't do or analyze it correctly if you're talking about it, and it will be different depending on whether S is the natural numbers or the rational numbers or the real numbers or the complex numbers or the Hamiltonian numbers or the Betty numbers, octonions in there somewhere. You're like, oh, those, yeah. So there's different types of numbers depending on what I'm talking about. Plus, these will behave, the ones that you're used to, plus, minus, multiplication, and division will behave differently on the set of all functions or the set of all numbers, etc. So in abstraction, a binary operation is going to be written as just star if we don't know what it's called, if you're just making it up, or I'm going to make some up. Not in this video. This is a quick tangent. I said quick in quotes. But what it does is it's a rule that creates new things. So it will take two elements, binary meaning two, and we will create a new element not necessarily in there. This is what closure, etc. will be. So this is why it has the reference to set. Subtraction is closed in the integers, but it's not in the naturals because there's no negatives in the naturals. So in general, what we do if we're just making one arbitrary one up, or we make a new one, eventually as this happens in math, if I wanted to find the multiplication in an elliptic curve and show why that's closed inside there, yeah, I need to create a star or something and say this is the multiplication in there, and then look at its properties. In abstraction, we're going to stick to plus, minus, multiplication, and division most of the time, with elements in the real numbers, and then functions and how to add and subtract functions themselves in the next chapter. So don't say so. I just killed the X. What a binary operation does is it creates new elements from old elements, and we'll see if they're in there. Let's do an example. Okay, so as in a quick example, you just use the first set, the only one that we've meaningfully talked about, the set of all the natural numbers 1 to infinity, the whole numbers, or the positive whole integers, whatever you want to start calling them, this guy. And then let's talk about plus on there and subtraction on n. So then what we can ask is closure, is what I'm going to get at right quickly as an example. Closure is if you take x and y in n, does that imply, question mark, that x star y in general is in n if you're having an arbitrary binary operation? Right now, this star, so that you hopefully nail down what I actually mean, is we're going to use that, and then or this one is what we're going to ask. And if it's a yes, you say closed under addition in the set of positive integers. Or if you get, then this is not closed. And I use plus and minus specifically because we'll start talking about it abstractly, or this, and you're like, why would you even start talking about that? It's like, yeah, plus and minus will show you that you have to start paying attention to that when you start analyzing an operation on a set. So do we have closure? Let's check. If I just take an arbitrary numbers in here, then x plus y, if they're in the natural numbers, is that in there? Well, if x and y are in there, if I start with x and y in n, x plus y, technically speaking, set theory, what we do is x and y would be sets with nothing in it, or the empty set, and these types of things. So then we would say x plus y is technically the set that has the cardinality of the union of the original two disjoint sets. So by definition, addition is, again, a positive integer. I kind of waved hands and snuck that in there as I was going because I'm making this shit up. I'm not a real mathematician. I just play one on the internet. I have a PhD. Just calm down. So this is true, so closed. To break something, and again, this points out right out the gate, if you're going to prove something's always true, you're going to have to, proof goes here, step 2, and then mystery. If you want to break something, all you need is one example. So closure so this was closure of addition, what we call plus on n. And now let's do closure of subtraction. Minus on n, which is take away pebbles. But what happens if you take away pebbles and you take away more than 0? Then abstractly, if I take those two guys in there, 4 minus 2 is equal to 2, which is a positive integer. But this, you can't Don't try to, just because one did, we have to know that it worked for everybody. So if I flip those around, 2 minus 4, so you can't just say then yes, closed. That's bad. You can't just check one thing. I need one thing to break it. This will, the other way will do it. This is a -2. Where's he? He's not in there. And so that's not in here. So not closed. All I need to break something or have something mathematically be false is have one condition, and it's not always true. If you want it to always be true, you have to go and be fancy pants and do step 1, steal underwear. Step 3, make profit. Step 2 is proof goes here, and it's much harder to prove things than to just tear the fucking world down. Next. Both pretty freaking interesting. What's an identity? What's an inverse? Okay, so now let's do the other half of that tangent. It's one direction, but they're oppositely directed. So let's do the definition of a binary relation on a specific set S, or it can be under relation on 2 different ones. We'll get into this later, but for simplicity right now, if you take 2 sets, then first of all, their Cartesian product, denoted S cross T, is the set of all ordered pairs ST. You've already seen that René Descartes Cartesian plane. This is ordered pairs, the 2-dimensional ordered pairs in R cross R. And so when the set is the same, we call R cross R usually R2, not the astromech droid, but the plane. And then this is after René Descartes, cogito ergo sum, I think therefore I am. He's like, maybe I should nail down where I specifically am in 2 and 3 dimensions. So he comes up with perpendicular or orthogonal coordinate systems, which you obtain from Gram-Schmidt process. We'll do these videos soon too, linear algebra. So I need that because what is a function? As a function is actually, well, we'll suppress a little bit, but it's going to be a subset of Cartesian product, and specifically it'll be a specific kind. So what is a binary relation for now? A binary relation on this thing is, it seems quite simple, and it is, but then it's confusing to hash out in your brain a little bit. But it's any subset of this Cartesian product. And we call it, so a binary relation F, we're going to call it instead of R because we're going to talk about functions. And then normally we write it in a slightly different notation that they give you from K to 12, and then not this way. So it'll hurt your brain a little bit. I'll do it right now. Skip this part, move it forward. So a binary relation F on S, so the S is going to be the S and the T, is any subset of S cross S. So what does that mean? It relates now 2 guys, and then it will be true and false. It doesn't create something new. It's creating something new, not in S. It's creating something new in the Cartesian product of S, and it's now going to be true or false in S, whether they're equal or not. Equals is a binary relation. Congruence is a binary relation, which are also have special properties we'll get into later in a different video. But for now, it's going to look like this, and you're like, a function is a specific type of relation, and relations are subsets of Cartesian products. So technically, yes, a function is a subset of a Cartesian product. What are you talking about? We're going to use this notation. This notation. What's the 3 most important things? What the frick, tie this together right now? Notation, notation, notation. So when I do this, I don't need you either. So normally if I have S cross S, we'll talk about R cross R, say. We're going to call it R2. So a binary, or we can talk about what we're going to do. Definition, or example, let S equal N. Then N cross N is equal to, and then that was also the segue we're going to, right now I just used and cheated and used set builder notation, so I'll do it right now. This means that this is going to be M and N such that, we're going to read this in set builder notation, M is in N and N is in N. It's actually the same one, close bracket, and there it goes right there. But you could write it also like this, because N is the same in this case. M and N are in N, close bracket. So this is set builder notation, because what did it just do? It built my more complicated set. So all you do is you write things such that their property is what set builder notation is. Bang, done. Now back to this. Beep, beep, beep. Let's go. So what is this? This now tells me that I'm going to look for certain, say, a relation on there. So if I take an M and an N in N, I want to know if M is related to N. This would be in, say, what I'm going to call a relation R, which is now a subset of N cross N. So some restriction of this thing. So what does that mean? For right now, this is the end of the tangent, and I'll do set builder notation, then we'll be done with this. What we're going to do is this. And we usually write y equals a function of x, and that would mean y f x. And then I was like, we should make it capital so that they know it's a set, but it's, there's the connection. We'll stick with this in your classes, and we'll do big F, little f, big hug, little hug, little hug, big kiss, little kiss. Encarnacion. This is from Nacho Libre. All right, so this will be our common notation of a function, but a function is a relation. A relation is a subset of the Cartesian product of a set with itself. Tangent over. Let's do set builder notation. Tap the sign. All right, just to end off this one, and then what we'll do is I'll segue into from that horrible tangent of binary relations, which is a subset, and we're starting to use all the notation. You start seeing none of this is tail chasing exercises. Everything I want is going to be a direct path for what we can talk about. And now you don't be like, what is he talking about, subset and everything? Yes, hopefully I did it systematically, and it's the things we're going to use to describe real numbers. In that, it starts getting more complicated. So let's do set builder notation, which is going to describe more complicated sets. So instead of writing out S as 1, 2, 3, 4, 5, 6, 7, 8 to a billion, I can just write clever notation. I'm going to abuse the fact that we're going to use inequalities, and you know what an inequality, the alligator eats the big guy. So I'm hoping that I'm going to abuse in a second for my example, and then we're out. So to describe a set, what we're going to do is we're going to write, so P of S is a property set S has. Like for the example I'll just use, because I just made it up in my mind as I was talking. I don't know where that comes from. What is the hard problem of consciousness? That's a different video. What we're going to do is we'll talk about the natural numbers, the whole numbers, and then we can talk about a subset of that, which is just the property of being a prime number, or the property of being an odd number or an even number, and then we can write that notation that way. So what is it? It's going to be x, elements x, such that is all this is read, and then the property that the set or the elements x in there have. So what do I mean by that? Immediately example, let S equal, or consider N, the whole set of numbers, and the subset S. So what do I want with that? How I'm going to write that in set builder notation is S will be equal to numbers that are positive integers. They're in here such that, and what do I have? X is prime, the property that it has. What will that be specifically? S will be 2, 3, 5, 7. We don't know yet. So there you go. Where's the end of that? I don't know. Nobody else knows. It's okay. So what does that do? This is such that. So elements such that their properties. And this will help us next time start the journey of the numbers quickly. What am I going to do before I segue to the next video? Quickly again, I did it at the end of the first video, I think, but 1, 2, 3, 4, no, 4 twice. We'll permute you after that for a second. But I started with these guys. We just talked about them all day today. So 1, 2, 3. And then I didn't even have to use inequalities. What's that going to be? or what's the next one? The next one we're going to get, the next one that's going to be coming into existence is going to be this guy, which is ellipsis -2, -1, 0, 1, 2. But I use the ellipsis, or you can write eventually, so I don't really need the set Bilder notation yet, but the next one's going to give me where I want Q is going to be, now it should become useful, because what's it going to be? Quotients of integers. So what we're going to do is we're going to say that Q is either m x such that x equals m over n, and m is in n is in z. So what does that say? This is all numbers such that it's the ratio of two integers where m is a positive. We'll move the negative to the top. If there's two negatives, they're going to cancel. You'll see you can't divide by 0. I eliminated 0 out of there and I did it backwards. You can't divide by 0. Or the way I could write this is, you can be fluent with this as long as you're seeing that this is just a such that. That's also the same set of numbers, which is the ratio of all integers such that the denominator is not 0. I'll see you next time. What we'll do is we'll build the rest. Okay, who's the rest? Then we're going to do R and then C. No. Beep, beep, beep. I had the 5, right? The guy that they didn't do where I wanted the complement, the only reason I said it. Numbers that are not rational but are real, or the complement of the rational numbers inside the real numbers, and then we'll find out that R is in fact the disjoint union of the rationals and irrationals. So every real number has a decimal repeating expansion or a non-repeating expansion. You can't have both. And then from there, I can permute those. And the next guy is complex numbers. There's no order on the complex numbers. We'll see you next time.